12 days from now, an interstellar visitor the size of a small mountain will swing past the sun, and for a brief moment, vanish into total silence. It's called 3I Atlas, and according to NASA's latest orbital data, it's racing toward the inner solar system at nearly 55 kilometers per second, roughly 80 times faster than a bullet. For most people, that would just sound like another comet making its way toward the sun. But this one is different. Its path is almost perfectly aligned with the plane of our solar system, the same invisible disk where all the planets orbit. That alone shouldn't happen. Interstellar objects, by their very nature, come from random directions in the galaxy. They don't politely glide along the planetary highway like this one does. So for scientists tracking its motion, that alignment raised an uncomfortable question. Is this just an extremely lucky coincidence? Or is there something else at play here? 3I Atlas was first spotted on July 1st, 2025 by the Atlas Survey in Chile, a sky-scanning network designed to catch hazardous objects before they get too close. When astronomers ran the orbital simulations, the results were startling. Its incoming trajectory wasn't elliptical, it was hyperbolic, meaning the object wasn't bound to the sun at all. It had entered our solar system from interstellar space, making it only the third confirmed interstellar object ever recorded, after Oumuamua in 2017 and Borisov in 2019. But even among those rare visitors, 3I Atlas stands apart. Oumuamua sliced through the solar system at a steep angle, like a spear. Borisov came in even more tilted, its orbit cutting diagonally across the planets. Atlas, on the other hand, slides almost flat along the ecliptic, tilted just 5 degrees from the planetary plane. If you imagine tossing a dart at a spinning globe and somehow hitting the same street every time, that's how statistically unlikely this trajectory is. And yet, that's exactly what's happening. This near-perfect alignment isn't just a geometric curiosity. It changes what's possible when the object meets the sun. A body approaching along the ecliptic meets solar gravity at a shallow angle, maximizing the time it spends close to the sun's immense pull. For any natural comet, that simply means it will heat up, outgas, and slingshot away. But if this were engineered, if someone or something wanted to use the sun's energy, this would be the ideal path, because this geometry allows for one of the strangest and most powerful tricks in orbital mechanics, the Oberth effect. In 1929, a German physicist named Hermann Oberth discovered something almost counterintuitive about rocket propulsion. He found that a spacecraft gains far more energy from a rocket burn when it performs it while moving at its highest speed, deep inside a gravity well. In plain terms, the same engine thrust that barely changes a ship's course in deep space could completely rewrite its orbit if performed near the sun, where velocity is immense. That's because kinetic energy increases with the square of speed. At perihelion, 3I Atlas will be moving at nearly 68 kilometers per second. If something were to fire a retrograde burn, even a tiny one, the sun's gravity would act as an amplifier, multiplying the effect of that maneuver exponentially. A change of just 1 kilometer per second at that point could translate to an enormous shift in orbital energy, potentially enough to alter its entire destiny. But to stop entirely, to go from a hyperbolic escape to a captured solar orbit, the object would need to slow down by roughly 20 kilometers per second. That's an extraordinary amount of deceleration, something no known natural force can achieve. And yet, the math suggests it's theoretically possible, if the object had its own propulsion system, and if it was designed to perform a controlled burn right at perihelion. Still, that's only half the story, because even if something did happen, we wouldn't see it. From October 22nd to November 7th, 2025, every major telescope on Earth, and even most in orbit, will be forced to look away. It's not because astronomers want to hide anything. It's a hard rule of physics and safety. When a target gets too close to the sun in the sky, it becomes invisible behind the solar glare. Point a telescope anywhere near it, and you risk frying your instruments with blinding light. Even Hubble and James Webb have strict avoidance zones. Hubble can't aim closer than 50 degrees to the sun. Webb is even stricter. It can't turn within 85 degrees. That means that when 3I Atlas reaches its closest point, the exact moment where any potential maneuver or anomaly could happen, no one will be watching. No telescope, no radar. No eyes on the event that could change everything. For nearly 2 weeks, it will vanish behind the solar curtain. And when it re-emerges in early November, all we'll have are the aftermath and the data. If its trajectory changes, if its outbound velocity suddenly drops, we'll know something happened in the dark. Just weeks before disappearing behind the sun, 3I Atlas will brush past Mars's orbit. Around October 3rd, 2025, it will pass about 29 million kilometers from the planet, close enough for the European Space Agency and NASA to try something risky. They turned the ExoMars Trace Gas Orbiter, Mars Reconnaissance Orbiter, and even Mars Express away from their usual tasks, aiming their cameras into the black to catch a glimpse. It was a desperate attempt. The object was nearly 50,000 times dimmer than their normal targets. Most images came back as noise, static, or empty frames. But even in that failure, there was meaning. If a body that large and bright was truly solid and massive, Mars's orbit should have shifted, even slightly, but it didn't. NASA's Deep Space Network logs showed no gravitational tug, no deviation in Mars's position, no sign of a 33 billion-ton visitor passing nearby. Something didn't add up. Based on its brightness, astronomers estimated the mass of 3I Atlas to be around 33 billion tons, one of the heaviest interstellar visitors ever recorded. But during its close pass with Mars, there was no detectable gravitational effect, no measurable pull on the planet, no residuals in the tracking data. For comparison, in 2014, comet Siding Spring, far smaller than Atlas, flew past Mars and still managed to leave a tiny gravitational fingerprint. So why didn't Atlas? One explanation is that its brightness is misleading. Maybe the surface is unusually reflective, a shell or layer of dust that exaggerates its size. Another theory is even stranger. It might be hollow, a shell-like object, spinning faster than any solid chunk of rock that large should be able to. And if that's true, then Atlas isn't behaving like a comet at all. It's behaving like something built. Spectroscopic data gathered in mid-September showed a large, expanding coma around the object, a cloud of gas and dust stretching over 180,000 kilometers wide. Measurements detected hydrogen cyanide venting into space at a rate of about 2 kilograms per second, along with traces of water vapor and carbon monoxide. These are all typical signatures of a volatile-rich comet. On the surface, the chemistry supports a natural explanation, an icy interstellar traveler shedding its frozen layers as it warms near the sun. But the details are subtle. The coma's symmetry is strange, almost too stable for a chaotic outgassing pattern. Its spin rate, measured by periodic changes in brightness, is higher than expected for an object of its estimated mass. And once again, its apparent lack of gravity doesn't fit the model. Taken together, the evidence creates a paradox, chemically natural but dynamically unnatural. A comet that looks like a rock, behaves like a shell, and moves like a spacecraft following a plan. As the countdown to perihelion ticks closer, scientists are split into two camps. One side believes 3I Atlas is simply a natural comet, albeit an unusually aligned and highly reflective one. The other believes it could be something engineered, designed to use the sun's energy to slow down and stay. If it performs a retrograde burn right at perihelion, the Oberth effect would multiply that thrust into a massive reduction in speed. It would go from a fleeting visitor to a permanent resident of our solar system. That possibility sounds like science fiction, and it probably is, but it's also mathematically sound. And over the next few weeks, as it vanishes behind the sun, the world will hold its breath, because when it comes back into view, we'll know which story is true. Will we see the erratic trail of a dying comet, or the deliberate deceleration of something that shouldn't exist? When 3I Atlas slips behind the sun, it will take the mystery with it. For those 13 days, the world's most powerful observatories, Hubble, Webb, TESS, even the Parker Solar Probe, will all look away. Every optical instrument is bound by the same rule: stay clear of the sun's glare or risk being destroyed by it. And so, for nearly 2 weeks, 3I Atlas will move unseen. No one will know what it's doing or what it's becoming. When it re-emerges, the sky will be filled with telescopes hunting for it. In Chile, the Vera Rubin Observatory will scour the horizon. In Hawaii, the Pan-STARRS array will run nightly sweeps. NASA's Deep Space Network will listen for radar echoes. And in orbit around Mars, the Trace Gas Orbiter and Mars Reconnaissance Orbiter will replay their scans, hoping to spot any shift in motion, even a fraction of a kilometer per second. Because if 3I Atlas really did use the sun to slow down, it would show up in the numbers first. A sudden drop in outbound velocity, far beyond what cometary outgassing could explain, would be the first red flag. Then the debris, small fragments moving with non-random trajectories, as though ejected with purpose instead of breaking apart chaotically. Each of these clues can be measured, checked, and confirmed. The evidence is either there or it isn't. And that's the beauty and the terror of data. When the blackout ends, scientists around the world will follow a simple list: the falsifiability checklist. It's the same method used to test any extraordinary claim. Collect the data, eliminate coincidences, and let what remains speak for itself. They'll look for a step-like change in velocity, a sudden clean drop that can't be explained by jets of gas, organized debris, fragments accelerating in lines or clusters, not drifting aimlessly, spectral shifts, a change in the light signature that could mean materials burned or were expelled in controlled patterns, unexpected signals, or atmospheric anomalies around the same period, radio blips, radar pings, or unclassified detections from orbital sensors. If none of these show up, the engineered hypothesis collapses. If even one appears, if just one number refuses to make sense, the story of 3I Atlas changes forever. This isn't the first time an interstellar visitor has defied explanation. In 2017, Oumuamua entered our system, a cigar-shaped rock that didn't behave like one. It accelerated slightly after passing the sun, as if pushed by invisible hands. Some said it was a hydrogen iceberg evaporating. Others called it a probe. The truth never landed neatly on either side. Then, in 2019, came 2I Borisov, the first unmistakably natural interstellar comet, venting carbon monoxide and ice in classic fashion. It proved that some visitors really are just debris from other stars. But 3I Atlas is a different creature altogether, faster than Borisov, more aligned than Oumuamua, and caught in a trajectory that gives it a front-row seat to the sun's raw power. And unlike either of its predecessors, this one will vanish at the most crucial moment. When it reappears, we may find the solar system has gained something new, or nothing at all. During the blackout, space agencies will stay quiet, at least publicly. But inside, the chatter will be relentless. Documents already circulating at NASA, ESA, and the US Space Force reportedly discuss contingency scenarios. What to do if the object decelerates, fragments in a controlled pattern, or appears to release smaller bodies. No one is talking about threats. Not officially, but everyone understands what's at stake. A catcher would mean the first permanent interstellar sample in human history. A deliberate maneuver would mean something else. Even without proof, rumors ripple fast. One leaked internal note described 3I Atlas as a test of observation limits. Another called it the most statistically unlikely approach geometry ever recorded. When scientists use language like that, it's because the data itself is whispering that something doesn't belong. Imagine, for a moment, the morning of November 8th, 2025. The first recovery images arrive from Chile, a faint dot lower in the sky than expected. Then another, offset slightly, trailing behind. A second, then a third, each fragment moving with perfect symmetry, not scattering, not spinning. Deep Space Network tracking shows an unexpected deceleration. Not much, maybe 10 or 15 kilometers per second, slower than the inbound speed. Not enough to stop, but enough to change everything. Social media lights up. News anchors call it the most significant celestial event since Oumuamua. Within hours, agencies issue statements urging patience, verification, calm, but it's too late. The idea has escaped the lab, because if something just used the sun to slow down, then someone or something just performed one of the most sophisticated maneuvers in physics. There's a quieter ending too. In that version, the data returns just as expected. The object reappears right on schedule, following the predicted outbound path, its velocity unchanged, its fragments scattering naturally, its coma fading just like any dying comet. No symmetry, no control, just another rock melting into the void. And maybe that's the truth. Maybe the alignment was a coincidence. Maybe the hollow shell was a trick of brightness and angle. Maybe the universe was just showing us another statistical outlier. A reminder of how easily our imaginations fill the gaps left by data. If that's how it ends, the story will still matter. Not because it proved alien intent, but because it revealed how thin the line is between wonder and fear. As the final days tick away, scientists, defense analysts, and amateur astronomers alike all stare toward the sun, waiting for November. Because on October 29th, 2025, at 1.36 astronomical units, 3I Atlas will reach perihelion. At that instant, it will be traveling at nearly 68 kilometers per second, threading the razor edge between cosmic chance and cosmic design. For 2 weeks after that, silence. Then, data. By late November, the numbers will begin to arrive. Orbital updates, brightness curves, spectral reports. Somewhere in those figures will be the answer. Did it slingshot away forever, or did it stop? That's the question the world will ask. And until we know, every telescope, every radar dish, every scientist will be holding their breath. Because if 3I Atlas really used the sun as a brake, then humanity just witnessed a maneuver we still don't fully understand. One that might prove, beyond doubt, that something else out there knows the rules of our universe even better than we do. For now, all we can do is wait. The data will tell us soon enough. But one thing's for sure, the next time you look at the sun, remember, something might be using its gravity right now to stop inside our solar system. Subscribe for updates when the new data drops, because the story of 3I Atlas isn't over yet.